Second, stay outside of the field near its edge and keep your eye on the landing target. Third, never turn your back on the field. This will prevent you from losing sight of the landing target. An S-turn landing approach allows the pilot to lose altitude by making a series of S-turns within a cone of safe airspace. The size of the S's decreases as the pilot loses altitude. By tracing smaller and smaller S's, the pilot loses enough altitude and lines himself up with the target for the final approach. When using this technique, turns need to be smooth and steady. Make sure you avoid steep turns near the ground. A series of figure 8 turns are used to lose altitude. The 8s get smaller and smaller so that the pilot can lose altitude and get in line with the landing field before his final turn. If the pilot overshoots the landing, he can trace different sized figure 8s to reposition himself. This type of approach is technically challenging. The pilot needs to know how fast his speed and altitude are changing in relation to the ground. This approach is ideal for a landing on a field surrounded by obstacles. The U, or standard aircraft approach, has 2 phases. This approach is also called constant aspect approach. The first phase. Without taking his eyes off the target, the pilot approaches the landing field along one of its sides. Though unusual, the pilot will be flying downwind during this phase. He needs to take this into account when assessing his airspeed. The second phase, the base leg. By looking at the target, the pilot will determine the best moment to make his first turn. The rest of the approach depends on this turn. The pilot needs to figure out how much distance he has left to cover, as well as the altitude he'll need before making the final turn. Whatever approach technique you choose to use, you should always end up with a long final. There are 2 keys to making a successful landing. The first is the wing stability. During the final, as the pilot gets close to the ground, he must keep the wing level and steady. And the second, the speed. A long final allows the pilot to increase his speed and build up energy that he can convert into a final flare. The flare will eliminate his vertical and horizontal speed and make a soft touchdown possible. Let's break down the phases of a landing. After entering the final approach, the pilot keeps his eyes fixed on the target with his arms up in order to increase the speed of his wing. Remember, however, to slightly apply tension on the brakes when turbulences are present. Only now can the pilot get into an upright position. He's ready to touch down at any moment. In order to land safely, the pilot must reduce his airspeed and ground speed to a minimum. This done by applying both brakes fully. This is called the flare. The flare is initiated 2 to 3 meters above the ground. This switch makes the wing pull out and produces a flare right before touchdown. An instructor will tell you when to make this switch by radio during your first flights. Be careful, each landing is different. The amplitude and the timing of this switch are determined by the wind speed. With experience, it'll become second nature. You'll discover the joy and comforts of making smooth touchdowns. sky is an ideal playground for adventure, but it can quickly turn into a very uncomfortable place. This is why learning how to fly also requires a comprehensive understanding of meteorology. Before tackling the broad topics of macro and micro meteorology, you need to be aware of the following basic principle. Warm, humid air is lighter than cold, dry air. Keeping this physics rule in mind, let's take a look at some meteorological fundamentals that will help you better understand your future playground in the sky. The atmosphere is composed of perpetually moving air masses. To better understand these incessant movements, let's take a look at a model of our atmosphere from a planetary perspective. Our planet has two major air mass zones. The polar air zones, located at the poles of the Earth, which extend into some of Earth's temperate regions, and the tropical air zone forming a belt around the equator, which also extends into Earth's temperate regions. Why is there a difference between the temperatures of the polar zones and the zone near the equator? The sun's rays are parallel to one another when they reach the Earth, but not all of them arrive at a 90-degree angle because the Earth is a sphere. As a result, the polar regions are put at a disadvantage since at high latitudes, the same amount of radiant energy from the sun is spread out across a larger surface than at the equator. By scaling this surface to the length of a segment, the difference becomes clear. Segment A is longer than segment B. As a result, the ground located in the polar zones heats up less, as does the mass of air directly above it. And since cold air holds little water vapor, the polar air mass is relatively dry. On the other hand, the ground located in the tropical air mass zone is heated more efficiently. The heat energy from the ground then warms the air mass directly above it, and because a warm air mass holds more water vapor than a cold air mass, it will be more humid. The transfer of heat energy between the sun and the ground, or the ground and the air, deserve a few explanations. First off, radiation. Radiation is the process by which the infrared energy emitted from the sun is directly absorbed by an exposed solid, in this case the ground. This type of energy transfer primarily works with solids. It's far less efficient with fluids or gases. The second type of energy transfer is conduction. As far as solids are concerned, this is the easiest way to transfer heat. If one end of an iron bar is heated, the heat will rapidly spread to the other end. In our example, involving the ground and the air, the energy transfer takes place between two different substances, a solid and a gas. Having stored up thermal radiation from the sun, the ground then heats the air it is in direct contact with. And finally, convection. This type of molecular energy transfer occurs in fluids such as gases or liquids. Air masses transfer heat between one another through convection. A warm layer of air will expand and rise. Now that you know a little more about the types of heat transfer from one substance to another, let's look at the two air masses found at our latitude. On the one hand, you have a mass of cold, dry air called the polar air mass. On the other hand, a tropical air mass composed of warm, humid air that is less dense than the former. These two air masses, though radically different in regards to their temperatures and humidity levels, remain adjacent to one another without ever mixing. The boundary between the two air masses is called the polar front. As long as these air masses move parallel to one another, the polar front is said to be stationary. But in many cases, cold and warm air masses overtake one another, causing unstable wave-like undulations along the polar front. As the amplitude of an undulation between the two masses increases, a low-pressure system develops. Weather forecast bulletins on television shows us satellite images of these low-pressure systems. The white clouds are spiraling around